All right, we're back. We're on page 140 of math analysis. We are talking about complex numbers in trig form. We just talked about multiplying them. We just did like a crazy problem where we saw, because the representations aren't unique in trig or polar form, we can get lots of different representations of the solutions to equations. So like here we found this was a possibility, but also this was a possibility. And that's something that we're going to run into kind of a lot, actually. This concept of like polar trig form, the lack of a unique location causes all kinds of generalizations that you have to make, but that's fine. Let's talk about division. So as we saw with multiplication, most of the rules about how to do things will fall naturally out of using Euler's formula. So here, if we take our complex numbers and we rewrite them, Z1 is going to be R1 e to the I theta 1. So this process is almost identical to what we did for multiplication, I theta 2. So if I divide them, Z1 over Z2 is going to be R1 e to the I theta 1 over, oh, I forgot R1, R2 e to the I theta 2, which will be R1 over R2. So we divide the moduli. Then what do we do to the arguments? So when you're dividing and you have the same base, you subtract the exponents. And then because they both have an I, you can factor that. So this is actually kind of interesting to me, right? So when you're learning first, like addition, subtraction, multiplication, division, addition and multiplication are just like empirically easier than subtraction and division. And it turns out that when you're dealing with these, when you're multiplying, you end up, multiplying the moduli and then adding. So the easy operations go together. And then division, you end up dividing and subtracting. The harder, more challenging operations go together. Which is also, it's like, I don't know if that helps you remember it, but it could. So I'm going to say this is R1 over R2. And then also, it's really similar to logs, where like division inside becomes subtraction outside, multiplication inside a log becomes addition between the logs. It's like, and it's logs are also just exponents, so it's properties of exponents. Everything comes back to properties of exponents with these. So I'm gonna write it like this: theta 1 minus theta 2. All right, so that's how we are going to divide them. So if you get lost or you forget, just remember Euler's formula and do it, and it'll just work out for you. So let's see. All right, we got two of these to do. So Z1 over Z2. Z1 divided by Z2 is going to be, so I divide the moduli, so 3 over 9, and then cis, subtract the arguments, minus 65. So this is going to be 1/3 cis, 240. 240 is what? 4 pi over 3. I don't have the unit circle memorized in degrees, so I have to convert everything, which is I have no regrets. 1/3. All right, so negative 1/2 minus root 3 over 2i. Ew, bad I. I. There we go. And I guess we should distribute. So negative 1/6 minus root 3 over 6i. Your calculator would have no issue checking that answer for you, so I'm not going to do it. And then here, Z1 divided by Z2, 24 over 2 is 12. And then cis, 150 minus 30 is 120. So again, I don't know why I'm rewriting this part. We get 12, and then cis 2 pi over 3. Just convert it. I mean, or I guess you could memorize the unit circle in, why would you do that though? You could memorize it in degrees. Negative 1/2 plus root 3 over 2i. All right, so negative 6 plus 6 root 3i. So that's division. So if you can multiply, then you can divide. It's basically one of those things. If you can divide, you can multiply. Not really the hardest thing, which is kind of awesome because, like, remember, division for complex numbers is just straight up weird. You have to like multiply by the conjugate. If you watch the videos, I messed that up in one of them. I forgot to take the conjugate, which was not great. So let's do this one more problem, which is leading into another idea. We're going to take a complex number to a power. So we're going to raise this to the third power. And then it says we're going to do it the hard way. So I guess there must be an easier way. So let's see if we can do it. So I remember, maybe you remember, if I have to cube, like a plus b cubed, let's say a plus b cubed is, so it's like 1, 3, 3, 1, the third row of Pascal's triangle. So we're going to go a cubed plus 3a squared. So the powers of a walk down from the highest to the lowest. So from 3 to 0. Powers of b walk up from 0. Oh yeah, b, sorry. Halfway through, I was like, what is b? Where is that even coming from? B walks up from 0 to 3. So this is technically b to the 0. This would be b to the first, 3a, b to the second, plus b cubed. So all along the way, the exponents add up to 3. So like 3 plus 0, 2 plus 1, 1 plus 2, 3 plus 0. And then this is 1, 3, 3, 1. So that's how we expand this. So let's just go for it. So it's going to be, so 2 minus 2i cubed. So now I'm just treating it as 2 plus negative 2i. Also, I almost lost my voice there. That was weird. So it's going to be 2 cubed plus 3, 2 squared, negative 2i, plus 3, 2 to the first, negative 2i squared, and then plus negative 2i cubed. All right, and then we just simplify this. So that's 8, 12, and negative 2 is negative 24i. 6, so what's happening here? Negative 4, so we get 4i squared is negative 4 times 6, so minus 24. And then, okay, so we have negative 8, I cubed, but I cubed, so we have I squared is negative 1, I squared is negative 1, I cubed is therefore negative I. So we have, what do we have? Negative 8, so plus 8i. Okay, so this, I don't know, if you haven't done that in a while, this is going to give me negative 8i cubed, which is negative 8 times negative I, which is positive 8i. And so overall, we have gotten negative 16 minus 16i. Now your calculator can do that without really thinking about it. So let me just make sure. It's like, I feel like I always need to make sure that you're remembering, like, oh, I don't know what I'm doing. Use your calculator. It'll just do it. Make sure you use the complex I though. If you, the imaginary I, if you use normal I, it's not gonna do it. Negative 16 minus 16i. So not bad, maybe not great, but it's just, it's like expanding binomials, right? Not a problem. So let's see. I think what I'm gonna do is cut this video here actually, because we learned to divide. We just raised a complex number to a power. Why did we do that? Well, I guess sometimes you want to do that. So keep in mind sort of that multiplying them is a rotation and also like a dilation, like you're getting farther from the origin or maybe closer depending on what you're multiplying by. So cubing it would be like rotate, 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 and then move, move, move. It's kind of an interesting thing. So anyway, we'll be back in the next video to do more with this, probably, I bet. Anyway, see you there.